In this video, we're going to do some practice problems relating to limits and continuity. So first, let's look at a big graph problem for limits. We have this kind of complicated graph of a function. We're going to answer some questions about what the limit is and also where it's not continuous. So this is a very complicated function. We're going to focus in on some specific x values. First, let's look at the limit of the function as x approaches -2. So what we're going to do is we are going to look at approaching -2, the x values, and we're going to look at the corresponding function values and see what value that's going to approach. And what we mean by what value it approaches, we are looking at what function value it's approaching. So it approaches that whole, and we're looking at the function value. And it looks like the function value associated with that whole is going to be -1. All right, so we're filling in the gap, filling in that hole. We have an answer of -1 there. All right, I'm going to erase each time, so we're not going to clog up this picture. Let's move on to the next one. X approaches -1. All right, so -1, we are approaching the x value, but what we're looking at is the corresponding function values. So if I get closer and closer to -1, we can see that the function values are actually going to blow up as there is a vertical asymptote there. It's going to blow up, and this is actually going to approach infinity. Both sides are going closer and closer to the same value, and that is infinite. So that is the value of the limit there. All right, next one. Let's look at the limit as x approaches 2. So same thing here. We have approaching 2, the left and the right. We're looking at the corresponding function values, kind of tracing our line, our finger along the function. And we get closer and closer to that whole. And the function value associated with that is going to be the -1. Note that the actual function value itself is at that point, that's going to be a value of -2. In fact, that's the answer to the next question, that the actual function value itself is -2, but the limit is different than that. It's -1, which means that the function is not continuous at that point. Let's look at 0 now. So as we get closer and closer to the x value of 0, and we kind of trace along the function, we are getting closer and closer to this point, which is going to be the value of -1 again. All right, and this is our uninteresting example because this is just the function value itself. It's just like I just found the function value. And that means it's going to be continuous at that point. All right, two ideas we didn't really look at in the first video, but we're going to kind of see later on as well, is the idea is what happens with limit as x approaches infinity or -infinity. So let's first look at infinity. What we're doing here is that we're saying that as x gets bigger and bigger and bigger, what happens to the corresponding function values? Well, we can see because of that arrow pointing down that these function values are just going to continue to go down and down and down. This is going to approach -infinity. This is the idea of the right end behavior, which we spent some time talking about in the pre-calculus review. This is the right end behavior of the function, also known as the limit as x approaches infinity of the function. The left end behavior of the function is looking at what happens when we go to the left. We look at the corresponding function values. And we can see that these function values are approaching the horizontal asymptote at y equals -2. So these function values are approaching -2. And this is the left end behavior. All right, so last question is, what values is the function not continuous? All right, where are the problem points? And there are 3 problem points. We kind of looked at all 3 of them already. -2, -1, and 2 itself. So where is it not continuous? At x equals -2, -1, and 2. Note that at -2 and 2, we have a removable discontinuity, also known as a hole. Up here, we have a vertical asymptote, and both of those mean that there's a discontinuity. Everywhere else, you can draw the function without taking your pencil off the paper. Even at 0, which is maybe the other kind of weird point, it's kind of a jarring sort of thing there, but we can still draw it without taking our pencil off the paper at that point. All right, onward. Next example, consider the function 2x over x squared minus 4. On which of the following intervals is the function not continuous? So what we're going to try to answer is, where are the discontinuities? Where are the problem areas? So this function has issues when the denominator is equal to 0. We have domain issues. And there's going to be no other point that there's issues, because 2x is a continuous function, x squared minus 4 is a continuous function. We know that the division of continuous functions is continuous. So this whole thing's going to be continuous except for when the denominator is 0. So that's going to be at x squared minus 4 equals 0. That's x squared equals 4. Take the square root, we get positive -2. So we are not continuous at positive or -2. So I should say x equals positive -2. So on what intervals is the function, which one of the following intervals is the function not continuous? The first one is continuous because it doesn't include -2 to 2. So that is not one of our answers. -3 to 1 is going to be our answer because it includes one of our problem points, -2. So it's not continuous on that interval. 0 to 10 is also going to be an answer because it includes +2. And lastly, the last one is not an answer because it does not include positive or -2. So which of the following intervals is the function not continuous? The middle two, because they include our 2 discontinuities. All right, let's look at the next one. Is the following function continuous? This is a piecewise function. We could graph this function to kind of see what's going on. So let's actually do that real quick. We'll do it very briefly. There is only one kind of interesting point here, and that is at the x value of 2. So 4 minus 2x is going to be the function or the function on the interval 0 to 2. So let's note this is a y-intercept of 4, a slope of -2. We're going to have this line. Note that another way to kind of do that is you could look at the two endpoints. This is a nice trick for piecewise function. When you plug in 0 into 4 minus 2x, you get 4. When you plug in 2 into 4 minus 2x, you get 0, and we're just going to draw that with an open circle because of the less than sign instead of less than or equal to, and then connect it in the way that we need to, which is a straight line in this case. Then we also know that this function is going to be x plus 1 when we're greater than 2. So let's do the second way. Let's plug in 2 into the function. 2 is going to go as 2 plus 1 is 3. So at the function value 2, we have 3. And then we can just kind of draw the graph of x plus 1. Maybe we need to graph one more point. If we plug in 3, we're going to get 4. We're going to go off in that direction. So the question is this function continuous? And the answer is no, because it is not continuous at x equals 2. There is a jump discontinuity at that point. Another way that we could have done this is not use the graph at all. We could just think about what is the limit of the function. We know that the function value, f of 2, is going to give us 3, because this is when 2 is included. But the limit as x approaches 2 of the function is, in fact, this is going to be does not exist. And actually, this is something we're going to see in the next video. We'll see why this is the case in section 1.8. So right now, let's just focus on the graph itself. All right, a similar kind of problem is another piecewise function. This time we're saying for what value or values of k is the following function continuous on the interval 0 to infinity. So let's start by graphing this like we did before. We have 5 plus 2x on the interval 0 to 1, and let's do the plugging in idea. As we plug in 0 to this function, we get 5 plus 0 is 5. When we plug in 1, we get 5 plus 2 times 1 is 7. So when we plug in 1, we get 7 up here, and we're going to connect those lines or connect those points at the line. That's the first part of our function. The next part of our function is that we have a line here, k minus x, on the interval 1 to infinity. So we know that k minus x, let's do the example. Let's let k equals 1. If we have 1 minus x, then we know that when we plug in 1, we'll get 1 minus 1 is 0. This function is going to look like this. And this would be not continuous. In fact, I should keep the colors a little bit uniform here. This would be not continuous because it doesn't match up with that function. It's like the example before. Let's say that we did an example like k equals 6. If we do k equals 6, so we have 6 minus x here. If you plug in 1, you get 6 minus 1 is 5. This function is going to look like this, which is also not continuous. So what really is happening here is that we need to find what value of k do we get that these two functions match up. And that's going to be when we have this graph. We know the slope has to be -1. We're trying to find what value of k will that be. And it's going to be at k equals 8. All right, now I didn't also just come up with that out of nowhere. We can do this completely algebraically. And this is going to be the way that we'll do a problem like this. We are trying to match up both sides of the graph. That means that we want 5 plus 2x and k minus x to be equal at x equals 1. So what we can do is we can just say, let's do 5 plus 2x at 1 is equal to k minus 1. We want those two functions to be equal. When we plug in x equals 1, we get this nice algebraic equation, which is 7 equals to k minus 1, or k equals 8. And that's how we can find this answer very quickly without even thinking about the graph. Though graphically, that's what we're kind of doing. We're trying to say that if we had k equal 8, we get this continuous function here. And there is only one value of k that works. This s here is a bit of a red herring. Right. Completely different kind of problem. Let's find this limit numerically. So this is a super weird function, 1 plus x to the 1 over x. Note that if you try to plug in 0, into that function, there is an issue. And to us, that's really what it's going to mean to be not continuous at that point. You have this 1 over x, 1 over 0 in the exponent. There's some issue there. Also know that we have no idea what this graph looks like. I couldn't tell you at all. And it's really not going to be a nice way to think about the limit. So numerically is our best option here. So we're going to draw a little table here of x values. And we'll look at the corresponding function values, where the function is 1 plus x to the 1 over x power. We'll just use a calculator to find these values. So we'll do, just like the example in the other video, we'll do 4 values here. We'll plug in -0.1, -0.01, 0.01, and 0.1. If we wanted to get closer, we could do 0.001 and go onward from there. All right, so when we plug in -0.1, we are plugging it into the function. We're doing 1 plus -0.1 to the 1 over -0.1 power. And this would give us 2.867. Let's plug in -0.01. If we plug in that value, we would get 2.73132 actually, or let's plug in 0.01. Let's see what we get there. This would give us 2.705. And if we plug in 0.1, we would get 2.594. And this is where I wanted to bring a good example of why it may not be the most useful to plug in values, because what value are we approaching from the left and the right here? Is it 2.7? Is it 2.7 something? Maybe we need some more values here. Let's try even something much more. Let's do negative 0.0001 and 0.0001 on the right. Let's see what we get when we plug in those. When we plug in negative 0.0001, we get 2.718. And we plug in 0.0001 positive, we get 2.718 as well. And there's some other numbers there. We can kind of get closer and closer to what value this is approaching. And in fact, this is approaching the specific value of E. E is about 2.71828, and there's some more numbers past that. And this is actually the value of the limit here. And we're going to see later on when we talk about E in more detail in this course that this is actually a definition of the value of E. All right, now it's very difficult to kind of see this and approach it. This is the downside of doing things numerically. We don't have a nice, specific answer of what this could be. If we plugged in values even closer, maybe we would get a little further away from E. Maybe it's close, but not quite E. It's not very clear, but it's a nice tool to kind of help us hone in on some value there. All right, and last example, let's think about the intermediate value theorem. So an example of that is, let's show that the function f of x equals e to the x over x plus 1 minus x squared has a 0 over the interval 0 to 2. And as here we're going to use the intermediate value theorem, and it may not be clear how we're going to do that yet. So note that if I do want to use the intermediate value theorem, we need f of x to be continuous. That is a necessity for that theorem. And note that, or at least continuous on the interval 0 to 2. So note that e to the x, x plus 1, and negative x squared are continuous functions. So f of x is continuous as long as x plus 1 does not equal 0, but that's only at x is negative 1. That's not in the interval 0 to 2. So f of x is continuous on the interval 0 to 2. And that's just because we know that exponentials and polynomial functions are continuous. And if we add, subtract, multiply, or divide, we get continuous functions as long as the denominator is not 0. All right, so how do we use the intermediate value theorem? What we're going to do is we're going to look at the endpoints here. We're going to look at f of 0 and f of 2. And we'll draw a little graph to kind of show what's going on here. So f of 0 is going to be e to the 0 over 0 plus 1 minus 0 squared. That is 1 over 1 minus 0. That's just a value of 1. F of 2 is going to be e squared over 2 plus 1 minus 2 squared. I've got to use a calculator to kind of see what this is going to be. This is going to be about negative 1.5. So how can this show us this is going to be a 0? There's going to be a 0 on this interval. Well, again, let's graph this function a little bit, what we know about it. We're thinking about on the interval 0 to 2, we have that f of 0 is 1, and we have f of 2 is about negative 1.5. And since this is a continuous function, no matter how you try to connect these dots, it has to cross the x-axis at some point, right? Y equals 0 is an intermediate value of 1 and negative 1.5. So therefore, I don't know what this function looks like, but it has to cross the x-axis at some point. Maybe it's somewhere else other than what I drew, but that means that there is going to be a 0. So this is since 0 is in the interval negative 1.5 to 1. That is f of b to f of a.